Hello guys, this is Puya. Just want to review the class that we had on wind energy. Didn't get to finish it, so I'm gonna finish it in this video. Many of the material here are either uh, gotten from the Wikipedia or other online resources, so want to acknowledge that. Um, so let's just start with the introduction. As you guys are aware of this, that wind power is not a new thing. It's been used for pumping water, grinding wheat or other grains, sailing ships or other applications. Wind power is basically extracting the power of wind from airflow using wind turbines. There are different kinds of wind turbines, mainly categorized in two categories: horizontal axis and vertical axis. We're going to see some pictures of that later in this PowerPoint presentation. You guys should be aware of that the ultimate source of wind is also solar energy, because with having solar, we get difference in temperature in other parts of this planet, and difference in temperature results in different in air pressure, and that's how we can get wind, by having a high pressure air and low pressure, and the wind blows from high pressure into low pressure. Power generated from wind is very sensitive to the speed of the wind. As we're going to see later, the power is proportional to the um, power of 3 of wind speed. Basically, power is proportional to cubed wind speed. And if the if the wind speed increases 2 times, the power generated from the wind speed is going to be increased 8 times. So you see how sensitive this is to any change in the wind speed. Some of the advantages of wind energy is basically it's a good alternative to fossil fuels. It's sustainable, it's renewable, doesn't have pollution, much pollution. It's a good resource for off-the-grid remote areas. So areas that are hard to get connected through the central grid, because they're remote and far away. So this is going to be a good resource. Many volunteers through Engineering Without Borders, they actually go to remote areas of different countries to install wind power plants for them, wind turbines for them. So that's one reason, because it's more expensive to connect them to the grid. It's distributed and plentiful, so it's not like solar or it's not like nuclear, that you need to have certain you need to be in certain part of the world like to take advantage of that um, resource. It's available in many parts of the world. It's plentiful, consumes no water. You don't need to wash the blades, but for example in the solar or like in nuclear, you need to use water. For solar, for example, you need to wash the panels to get rid of the dust or sometimes snow. It doesn't have any greenhouse gas emission, so no GHG. It has relatively small footprint, and it has minimal net effect on the environment. So as opposed to hydro dams that might cause damages to the ecosystem. And because it's plentiful, you can install power plants, wind turbines in many parts of the world, as long as there is wind in them. Some of the disadvantages is variable and intermittent. Like it basically, like you can't plan it that well. Of course, some wind farms in offshore, it's more variable and less variable and more stable. But onshore wind turbines are very variable, so you can't plan that much. It's not dispatchable on hourly, daily, or seasonal basis. It means it's not controllable. It's not like that you can bring this power plant into, or bring this unit into the grid whenever you want. it depends on if you have wind or not. It can cause instability in power system, small signal stability, dynamic stability, mainly because it generates active power, but it absorbs reactive power. So you need to have like some extra equipment like capacitor banks or other filters or other active filters or power electronic equipment to compensate for the reactive power absorption. And because it has an induction machine, the induction machine sometimes gets stalled. So that's another problem with the instability in power system. Its capacity factor is low. Capacity factor is basically the ratio between the actual energy that can get generated from the unit compared to its rated compared to its rated power. So, for example, a wind turbine can be rated 2 megawatts, but the actual energy that you get from that wind turbine throughout the year is not going to be 2 megawatts. It's going to be less than that, much less than that. It's because you don't have wind all the time. So typically something between 20 to 50%. 50% is very good. 20% is typical. So if you compare it to nuclear or hydro or thermal power plants, you see that like for them, like it's between 90 to 95%. So its capacity factor is very low. It's basically you have a very huge initial cost, but you're not taking advantage of it to its maximum. So one thing that we can do is basically uh, have hybrid power plants. So it's using the same infrastructure, using the same transmission lines for two different power plants. One can be, for example, hydro, one wind, one can be wind, one solar, and so on. It also generates a lot of noise, so like it in residential areas, it can cause some problems for the residents. So here you see a schematic, a picture of a typical wind turbine. Because the direction of wind is not fixed, we have to have some control mechanisms to basically rotate the turbine according to the speed of the wind and the direction of the wind. So you see here that there's an anemometer here, basically measuring wind, direction, and speed, so that we can adjust the direction of the wind turbine. There are multiple control mechanisms here. You see two of them. There's a yaw control here, so there's a motor here with gearboxes that can change the direction of the turbine, so like it can move the direction of this turbine. There's also pitch controls that can also like change the angle that the wind hits the blades of the turbine. So to get the maximum, you can think of blades of wind turbine as an aeroplane wing, and sometimes you see that aeroplane wing like when they try to stop, or like when they're trying to just go up, like you can see that like there's some small changes in the blade in the wings of airplane. The same thing happens for the blades of wind turbine. So it can basically rotate based on the direction of the wind that we can measure using an anemometer. It has a generator. This can be either induction generator or synchronous generator. Mostly induction generator, but synchronous generators can also be used, as we will see later. If you use induction generator, you might not need a gearbox, but like with synchronous generator, to adjust the speed of the wind to the frequency that you should provide to the grid, we need to have gearbox here. So this is basically to adjust the speed of the rotational speed of the shaft of the generator. Am I missing something? There's some breaks. So sometimes like you need to take the unit out of the operation, so that there's some break here. And basically that's what a typical wind turbine looks like. There are some sensors to measure wind and direction, speed of and direction of the wind. most people don't realize how big a wind turbine blade can be. Nowadays, it can be up to the range of 250 meters, and it's gonna be larger in future as the technology grows. You see that like throughout the years, um, the the length of the blades have increased because the power that you can get from a wind turbine is linearly proportional to the diameter of the sorry, it's not linearly, it's proportional to the area of the circle. So the larger this area is, the circle area is, the more power you can get from this wind turbine. So again, like it's linearly proportional to the area. So it's going to be proportional to the square of radius or diameter. And you can see here a comparison between some monuments with a typical wind turbine here. So they can be very, very large. And as technology goes, a technology of construction technology and like material technology goes ahead, like we can come up with more wind turbines. One of the problems with having longer blades is like its transportation. So that's something that has to be addressed, like how to transport such long blades. Can we just like decompose them into many parts and assemble them at the site, or how can we ship them? Um, in most of the wind turbines, they use induction generator because wind speed is variable. So induction generator can be a good option for here. Otherwise, we have to use gearboxes to adjust the speed to the frequency of the grid. As you can see from the torque velocity curve of an induction generator, it can work in the motor mode, or it can work in the generating region. When we're using the induction machine as a generator, its speed, it's going to be super synchronous. It's going to be higher than the synchronous speed. Slip is going to be negative, and machine runs as a generator, and rotates faster than the stator field. Um, and here, induction generator, it generates active power, as I mentioned earlier, but it consumes or absorbs reactive power. So that's one of the challenges that we have to address. It's not similar to synchronous machines, so that can cause some instability, some stallment, and we have to address that using some power electronic equipment or filters or capacitor banks and whatsoever. So when we want to build a wind power plant, we just don't have one turbine. We put many of them together, and we call them wind farms. We can have onshore or offshore wind farms. Offshore wind farms are more expensive. You definitely have to do a lot of under the water construction, and like transmission cables has to be under the water. Um, it might damage the environment a little bit. So it's more expensive, but it's more stable because the wind is more steady over the sea or over the lake or over the ocean. The onshore ones are cheaper. There has to be a certain distancing between wind turbines. So if they're in the direction of the wind, typically 5 to 9 times of the rotor diameter. If they are perpendicular to the wind turbine, like has to be 3 to 5 times of the diameter. So this is gonna be for safety reasons, and also like to make sure that the wind speed, um, wind goes back to the original speed before it hits the next wind turbine. Um, it's a good strategy to, as the capacity factor of the wind turbine is low, it's a good strategy to use the same infrastructure for 2 or 3 power plants. So maybe like having a hybrid power plant, having a solar and hydro at the same time, so you can use the same, let's say, transmission lines or cables for both of them. And it's mainly because wind is like highly intermittent, like in shorter times. Over the year, it's like more steady, but to take advantage of the full rating of all the equipment that we install, sometimes it's better to switch to hybrid power plants. Some power management technologies, techniques to address wind variability. So having extra capacity to what we need, so that like we never have shortage of power. Geographically distribute the wind farms in different places, so that if one place doesn't have enough wind, the other place can compensate. Have some dispatchable backup sources, so when there's no wind, you can have still power from another source, a non-wind source. So most utilities, they have contracts with neighboring utilities so that they can either export or import power. Usually like the peak time of different regions, different utilities is different. So usually what utilities do, they import power during their peak time and export it when they don't need it. You can use the energy that you get from the wind turbine to charge electric vehicles, so like they can be used like in vehicle to grid strategies. And also there are two different schemes: demand response or supply response. For wind turbines, maybe demand response can be better, so that we can shift some of the demands when there is wind. So for example, if I want to use an analogy, like if you want to buy something, sometimes you need something, you go buy it. This is demand response. But sometimes you know that you will need it in future, but you don't need it right away. Okay, so in that case, you basically go and like buy it for future. That's supply response. Also, weather forecasting can be helpful, so that we know when the wind is coming, although like this is not very accurate still. As I mentioned, capacity factor is defined as the ratio of the actual energy generated over the year to the maximum possible energy to generate, to the actual rating of the wind turbine. Because wind flow is not constant, we never can get the actual rating. So there is always a fraction of the rating that we can take advantage of. That's called capacity factor. The theoretical maximum energy is the capacity factor multiplied by the hours of operation. So as an example, you see here a 520 terawatt hour rated wind turbine has a capacity of 282.2 gigawatt. Okay, what is the capacity factor? So the rating, you have it. So the rating goes at the bottom in the denominator. And if you want to calculate how much power actually get generated, you can multiply the gigawatt thing by 365 days and then 24 hours, and then divide 282.2 times 365 times 24 by 520. And if you do that, the answer should be around 20% or 21%. Usually this is a typical capacity factor. The goal is to reach it to 40 to 50% capacity factor. So with the advancement that we have in the technology, that can be possible. It's I think it's already possible. Wind energy penetration is basically how wind energy is going to be used in the grid and can be used in the actually production of energy, in the generation of energy. So since 2005, wind energy um, became economical. So like it's comparable. It has a comparable price. If you consider the infrastructure investment, it's comparable to the price of fossil fuel. And so far, we have only 4% wind energy as part of the generation power in the energy sector. In Canada, for example, they want to raise that to 20% by the year 2025. Factors that can affect maximum wind penetration, it can be political and technical factors. Some of it can relate to configurations and the technology advancement, pricing of wind power and pricing of other fossil fuels, or for example, or other resources. Storage capacity, so similar to solar power plants, we would like to store the energy as possible so that like we can use it later. Um, the cost for connectivity to the transmission grid, so that like we can evacuate the power generated by the wind turbine. And smart control techniques. So for example, I showed you some control techniques that are used for wind turbine. That's the mechanical part. Also like the electrical control techniques for the active and reactive power control. Those are some strategies that can help with the wind energy penetration. Making reserve capacity available and switch to demand response schemes. You can also see like a comparison between um, different resources available in different countries. So as the capacity factor is very low for wind turbines, it doesn't make sense to have like a high um, initial investment only for 20% of rating power. So it's a good strategy to use hybrid uh, power plants. And system operating cost can also increase with any increase in wind penetration. It requires more planning, variations, and configurations. Sorry, there are some typos here. I'm sorry. It requires more planning. Now we get to some calculation. This part can be a little bit challenging, but we basically want to see how kinetic energy of the wind can be converted into the mechanical energy. So here you see that we have wind blowing from this side, and it has some kinetic energy, half of m times v1 squared. That would be this kinetic energy. And as it goes through the blades, it hits the blades and then goes through it. Over here we have the wind getting out of here. It's going to be expanded by the blade. So like if it just, let's say, like goes here, it gets expanded, it loses pressure, and it also reduces the speed is reduced. And the difference between these two kinetic energies is basically converted to mechanical energy that later on can get converted to electrical energy. So this is what I just explained. And according to the Bernoulli principle, as the area increases, if you have a fluid going through a pipe, or for example to any platform, as the area increases, the velocity decreases. So here in the opening of this pipe, if the velocity is v1, over here v2 is going to be bigger than v1, and over here v3 it's going to be smaller than v2. So that's why like here when wind hits the blades, it loses some speed. The speed cannot become zero, so we cannot convert all of these kinetic energy into mechanical, because if the speed becomes zero, then the blade stops turning, rotating, right? So like it's not possible. in the beginning, um, if we plot mechanical energy with respect to the V2 over V1, V2 is the speed after, and V1 the outgoing speed, and V1 is the incoming speed. If 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 V2 is 0, we get no power. If V2 becomes V1, we get no power. We want to know like what's the maximum? Where's the point that we get the maximum power out of the wind turbine? What's this ratio should be so that we get the maximum power? So that's why like we have these calculation. I got it from a very nice guy from YouTube. So like he explained it very well. So I'm using the same method here. I wrote the equations here. You can see that mechanical energy is kinetic energy of incoming kinetic energy minus outgoing kinetic energy. So it's going to be half of m times v1 squared minus v2 squared. Maybe I should also like introduce some of the symbols that we have. A sub t is area of turbine. V sub t is velocity of wind turbine at the turbine. So if this is incoming, V1 is incoming, Vt is right here, and V2 is outgoing. And Q is the flow rate, which is the unit. It's going to be mass divided by time, so kilogram per second. And rho is the air density, which is at 1 atmosphere, it's going to be 1.225 kilogram per cubic meter. So power is changes of energy over time. So the rate of change of energy over time. So it's basically dE over dt, or we can say delta ME over delta T if these steps are small enough. So if we do this calculation, it's going to be 1 over 2 m over delta T, which is going to be exactly equal to flow rate times v1 squared minus v2 squared. And flow rate, we can relate it to the area of the wind turbine and the velocity at the wind turbine and the density of air. So Q is going to be rho AV. So we can just replace this this formula with this formula. So keep this one in mind. So the power generated from a wind turbine can be equal to this 1 over 2 rho AVT times V1 squared minus V2 squared. Now we'll try to simplify this. So now let's just like forget about this part. Now let's look at the force. The force of the wind on the blades, it's going to be m times acceleration, and acceleration is derivative of velocity over time, so it's going to be m times delta v over delta t. Now we just like reshape it, so we write it as m over delta t times delta v. Again, this is going to be q, right? So it's going to be equal to rho a times vt v1 minus v2. And power is F times V in a rotational mass, or you can think of it as power is F times D, which is going to be work divided by time, right? So energy is work, or energy is F times D, right? Force times distance or dislocation. And power is energy divided by time. So if we simplify that, it's going to be F times speed. So it's going to be this value, which is F times speed, okay? And this is basically what we end up with, okay? I want to make sure that I didn't make any error here. I think this is wrong. I'm using the same thing. Sorry, this is wrong. This should read rho a v2 squared times v1 minus v2. Okay, let me correct this. It should read rho a v1 squared times and this should be Vt squared. Let me grab it from here. So this is one power. I'm sorry. And this is another power. If I make them equal, so if I make this one equal to this one, then we see that, there you go. We see that the velocity at the blades, it's going to be half of the incoming plus outgoing velocity. And if we replace that in this formula, we come up with this equation. Okay. Now, what we wanted to find the maximum power that we can get, or the maximum energy we can get. So at this point, the slope is going to be 0, right? So we take derivative with respect to this variable v2 over v1, and if you solve that, you see that v2 over v1 should be equal to 1 over 3, so that we get the maximum power. And the maximum power that you can get, it's going to be equal to 8 over 25 times rho a v1 cubed, while the input power, it's this much, half of rho a v1 cubed. So the maximum power that you can get from a wind turbine, it's going to be 16 over 27. Like the maximum efficiency, like I'm talking about the maximum capacity factor, it's going to be 16 over 27. So close to 0.6 or 60%. That's called Betz limits. That's the name of the person who found or who did this calculation. So it basically shows that the maximum power that you can get extracted from the wind, it's going to be 60% of, less than 60% of the input power. That's called Betz limit. So there's some 2 questions for you that based on these formulas you can solve. Let's talk about a little bit economics of wind energy. As I mentioned, wind has reached grid parity since 2005. It means that like its cost is become equal or sometimes less than the fossil fuel energy generation. Its capital investment, the infrastructure is very intensive, but it doesn't require any fossil or any fuel cost or any water. Its price is more stable, as it's not like that much affected by political factors, and its marginal cost is very low. It means that if you want to increase your generation 1 kilowatt, depending on where you are, like you need to just like basically add few more cents to your investment. Its average total cost is going to be much higher because it comes with other equipment, control methods, control equipment, grid connection and construction and other things, salaries for the staff and so on. Factors that affect the wind energy cost, it's basically wind speed. Where you have like higher wind speed, it's going to be cheaper, the lower the cost. In turbine design, it's going to be very important, and different configurations. So in certain areas, according to the application, according to the wind speed, certain turbine design, it's more efficient. So this is usually done using software, simulation software. So like this part is probably the most important part of designing the wind turbine, the design of the blades and like making it more robust and also like efficient, and rated capacity of wind turbine that we just talked about. The location is important because of the wind, and the capital cost, like depending on where we are, like how much cost we have for the infrastructure and like what kind of infrastructure we need, do we have it available or not available. So these are the factors that affect affect the wind energy cost. Typical distribution of cost. The mechanical parts, the turbine and mechanical parts has the highest portion, 65%, the construction around 12%. Electric parts, it means like generator and the electrical equipment, 8%. For the grid connection, around 5%. Staff salary, project management, managing the whole thing, around 10%. So this is the breakdown of the cost for a typical wind power plant. There are some small scale wind power. So this is like, again, I mentioned that for remote areas, sometimes you just want to have a small scale wind power plant. So these are like vertical axis, as I mentioned, like this is like horizontal axis, this is vertical axis. And you can see the difference in terms of their configuration. So the lens turbine, I think it was invented in Japan. That's good for small scale application. But what we call a small scale is basically less than 50 kilowatt generation. It can be a good alternative to fossil fuel, to diesel generation in isolated or remote areas. When you want to design a wind power plant, you should be careful with the aerodynamics of the turbine, the deflection of air by turbine. So similar to solar power plants, that we don't want to have any reflection. We want to make sure that like the aerodynamics is designed in a way that we don't have that much deflection of air. Blade shape and dimensions is important. Strength to resist forces. So we don't want, excuse me, we don't want the blade to break or get deformed with wind. And design of the whole wind energy conversion system. Turbine design usually is done by computer simulation. And if we have a very good design in modern wind turbines, we can reach up to 70 to 80% of Betz limits. So Betz limits was 60%, 70% of that can be like around 40% capacity factor, which is a good thing. The types of generators that we have for a wind turbine, they're classified in 4 types. Type 1, it's an induction generator with it's a generator with a fixed speed. Type 2, it's again a generator connected directly to the grid by this like here, like it's directly connected to the grid, so it has a fixed speed. You can see here like you have capacitor banks. For the type 2, it has a little bit of variation in terms of the speed, because you can change the armature resistance. So based on that, you can change the speed. But type 3 and type 4 are, type 1 and type 2 are becoming obsolete. They're not used that much anymore, unless in a specific application. Type 3 and type 4, especially type 3, is more popular. Type 3 is called doubly fed induction generator. So it's an induction generator that gets connected to the grid. This is like one feeding path for it. It also gets connected to a grid using an inverter and a rectifier. The other way around, sorry, rectifier and inverter. If I look at it, it's going to be inverter and rectifier. So you can control the speed in this case. The same thing can be happening directly, but it's more costly. This is type 4, and in some type 4 you can use synchronous generator as well. So here it shows you some of the advantages and disadvantages of each type. I'm not going to go through any of all of them, but type A and B are mostly fixed speed. Like type B, it's a little bit variation in the speed, but not that much. So it's an upgrade to type A. But type 3 and type 4 are variable speed. This one has a full scale frequency converter. It means that your converter has to have exactly the same rating as your machine, but in this case, your grid. But in this case, no, it can has like a partial scale frequency converter. So it's basically you're trying to convert AC to AC, a different frequency to a different frequency. It can be done like using a combination of rectifier and inverter. The same thing that's happening in type 4, but this one is more costly. It's very more expensive. So type 3 and type 4 are both variable speed, but type 3 is more affordable than type 4. That's all I wanted to share with you guys. I'm gonna end this meeting. Thank you so much. Bye bye.